Alright, this is section 3, all about acceleration. Alright, we see that acceleration is just when the rate of change of velocity. And so, if the velocity is changing, we said that that an object is said to be accelerating. And so, we have to go back and remember what is the definition of velocity. And so we know that velocity is how fast something is moving, which of course we say, fast means speed. And then it's also the direction, right? Because velocity is speed with direction. So acceleration is simply the change in speed or direction of an object. So acceleration includes objects that are speeding up, which is what we typically a lot of times think of. We're like, put the pedal to the metal, we're accelerating. But it can also be slowing down, which a lot of times we use the word deceleration for, but that's also included in acceleration. But the thing we don't think about a lot of times is that we can actually be just changing direction, and that's actually considered acceleration. Like for example, here we have our circular diagram that we've seen earlier. Just by going in that circular direction where we're changing velocity, we are actually accelerating, because if we're changing direction, we're changing velocity, and if we do that over a certain period of time, then we are considered to be accelerating. So keep that in mind, that changing direction, slowing down, speeding up, all those things are considered acceleration. For objects traveling in a straight line, we can look at a speed time graph just like we can for, like we did with our speed. Basically we can look at graphs for acceleration just like we did for speed. It's just that the slope is going to be acceleration this time instead of it being speed, because we're graphing speed and we're graphing time. So anytime we have a line where it's not straight, those are going to be accelerations. So we have a fancy equation for acceleration. Acceleration is the change in velocity over time. Now it looks kind of funny because the abbreviations look like this. You have A equals VF minus VI over T. Now it looks kind of funny, but just all you need to know is that VF just stands for velocity final. And you just have to think of that as like your stop velocity. Like something's traveling and it stops, so that's the velocity it stops at. Or if it's talking about a problem, like what did the problem finish at? What was the final velocity of that particular object? And then you have velocity initial. What was the velocity that it started at? So was it moving? Was it standing still when you started the problem? Okay. So those, those are just your two things. And of course then, so you're going to subtract those two. So keep in mind that your top or your overall acceleration can be negative. So A can be negative. So just keep that in mind. So there's some little side notes. Alright, let's try an example here. So we said that our equation is A equals VF minus VI over T. Where we went, let's see. So these are our variables. Okay. Now, acceleration is going to have the units of meters per second squared. Okay. VF is going to be 8 meters per second, VI is going to be meters per second, and time is going to be seconds. Now, so these two you're going to distinguish by having to read the problem and analyze. This is going to be one of those problems, acceleration, you have to focus on and read. So let's see. Suppose a jet airliner starts at rest, that's kind of a key word there, at the end of a runway and reaches a velocity of 80 meters per second in 20 seconds. What is the jet's acceleration? Okay, so the big thing I can already put is 20 seconds. We know that the time is 20 seconds. That's easy. Now, they give us 80 meters per second. That's the other number. Now it says it reaches this velocity. That means it ends at that velocity. So our VF is 80. Now it says it starts at rest. So that means we're starting at 0. So that means we're finding A. So A is going to be equal to 80 minus 0 over 20. Or basically 80 over 20, which is going to be 4, and the label is going to be meters per second squared. Now something I want to point out here is that there's this right here in the problem. Remember that velocity has a direction, and so acceleration should technically have a direction. So if possible, you should have a direction with it. Okay, let's try another one. Alright. Get all our variables. A skateboarder moving in a straight line with a velocity of 3 meters per second and north comes to a stop in 2 seconds. What is the skateboarder's acceleration? Okay, so we have is moving in a straight line with a velocity, comes to a stop in 2 seconds. So it starts out moving, so initially it's going 3 meters per second. Then it comes to a stop, so its final is 0, and it does all this in 2 seconds. Okay, so again we're finding acceleration, and so all we have to do here is we go V final. Remember your equation is V final minus V initial over time. So A is equal to 3, oops, sorry, did it backwards. V final, which is 0, 0 minus 3 over 2. So it's negative 3 over 2, or negative 1.5 meters per second squared. Okay. So again, here's an example of where it could be negative, and that makes sense because something is slowing down, it's decelerating. Okay, we'll try one more just for funsies. Okay, A equals VF minus VI over T. So A, VF, VI, T. Okay, so a bicycle starts at rest, accelerates to 2 meters per second squared. Oh, you know what? We're not going to do this one. I'm not going to go to that scope, so we'll just go on. Okay, we're going to talk about centripetal acceleration. Centripetal acceleration is acceleration towards the center of a curved path, meaning that we accelerate around this curved path here. There is a force that actually pulls us inward. We're going to talk about that later. But the acceleration of this car actually goes inward the entire time. And that's called centripetal acceleration. Now, something else interesting is that when an object accelerates, it actually causes things to move, and in fact that has a lot to do with projectile motion. So if you've actually tossed something to someone, hopefully you've noticed that when you've launched an object, you notice that it comes off a curved path and actually then fringes down to the ground. So Earth's gravity actually causes a type of acceleration that causes objects to follow a curved path. So when you throw a ball, the force exerted by your hand causes the ball to be released, or an object to be released. So that gives it horizontal motion. Oops, sorry. So you have a ball, you release it. It gives it horizontal motion going that way. There's no force once you release it pushing it forward, because once you release it from your hand, there's nothing giving it any more push. So there's no more force going in that direction. So its velocity this way is constant because there's no more force. So it's traveling at a constant velocity. And of course right now we're not looking at air resistance or anything like that because it's going to affect it. But so if there was a constant velocity though, it would travel in this direction forever, meaning that there would be nothing that would stop it. But gravity comes in and actually puts a downward force on the object. So because gravity does, it gives it vertical motion and it actually causes it to accelerate. So gravity is what causes the actual acceleration. There's no vertical or there's no horizontal velocity. That's kind of the key there. There's no horizontal velocity, but there is vertical velocity. And that's what gives an object a curved path when you throw it. So a ball has constant horizontal velocity but increasing vertical velocity. So gravity causes what's called an unbalanced force, and it causes it to go not only forward but from forward to downward. And so that's what causes a curved path in a traveling object that's been thrown. Amusement parks are a great example of something else that uses acceleration to give us thrilling, harmless rides. Physicists, they use engineers, they use physicists in order to ensure that roller coasters give us high speeds and accelerations that are safe but harmless. They use multiple drops, loops that allow for g-forces that are safe but harmless. And so that's just another example of, real life application of physics, that they take the information that we might learn, like stuff that we are learning in this class, but putting a practical application to it. So this stuff is useful. It's used in the real world. They take this stuff and make it, fun for us. So, and that's the end of our notes for section 3. Oh, not quite. So, just talking a little bit more about roller coasters. Sorry, I went on a little bit more about roller coasters. I forgot there was one more slide. So, just basically that I'm talking more about that if you go around sharp hills, you go around loops, that because of gravity and acceleration, it makes the amusement park rides more fun. So, now we're at the end of the notes, and so we have finished up chapter 2, and we'll be ready for our test.